Hey all you wonderful viewers out there, my name is Matt and welcome to Physicalculus. Given that this is my first video, before I jump into solving any problems, I'm just going to lay the groundwork and expectations for my channel. First of all, I'm not going to be teaching any of these concepts. I'm merely going to be applying these concepts to solve problems. So I hope that you can learn something from these videos. I hope that these videos are helpful for you guys, but I will not be lecturing on them or teaching them in any sort of organized way. Secondly, I think it's important that I tell you guys how I'm going to structure these videos. So I'm going to be doing the algebra-based physics problems and the calculus-based physics problems separately. These two problems that I'm going to start off with are both algebra-based. Hopefully next week I can get a video out explaining how to do some calculus-based physics problems, but that's how it's going to work. They're going to be separate. Additionally, I'm going to try to do some pure calculus-based problems, some pure calculus problems. However, those are going to have their own separate videos. So the algebra-based physics problems and the calculus-based physics problems are going to have their own separate videos, and the physics problems and the calculus problems are going to have their own separate videos, if that makes sense. I just think that that will be easier for me keeping track of everything and uploading things for you guys. Thirdly, I'm going to be following significant digits in my calculations. So I'm going to assume that you guys are at least a little bit comfortable with significant digits. If you're not, I would highly recommend doing some research on them or checking them out because you might be confused why I give my answer a certain way otherwise. I'm going to try to leave a link in the description down below if I find a site that I think explains significant digits well. But yeah, I'm going to try to follow significant digits. Fourthly, all of the problems that I'm going to be doing, at least for my physics videos, are going to be adapted from Sears and Zemansky's University Physics with Modern Physics, specifically the 14th edition by Young and Friedman. This is a great textbook. It has lots of problems to work on, and I love it, but I want to avoid copyright infringement, so I'm going to be restating them in my own words, and the numbers have been changed. So the method that I'm going to use I know is correct, but the numbers have just been changed to avoid copyright infringement. Young and Friedman, Sears and Zemansky, if you see this, please, please, please don't copyright strike my video. I'm not trying to copyright strike I'm not trying to, I'm not claiming these problems as my own. So please, please, please do not copyright strike my video. With all that being said, let's jump right into this problem here. So, this problem is adapted from Chapter 5, Problem 74 of Young and Friedman's University Physics textbook. And it says, two blocks M1 and M2 are connected by a massless rope passing over a frictionless, massless pulley. M1 rests on an inclined plane at angle alpha equals 43.1 degrees above the horizontal. The coefficient of kinetic friction between this block and the plane is mu k equals 0.30. M1 equals 22.0 kilograms. What is the mass of M2 if it descends 11.0 meters in the first 2.75 seconds after it is released from rest? So, when starting any physics problem, especially a problem involving forces, we want to make sure to draw a picture of what's going on. It doesn't have to be a good picture, it just has to be a rough sketch of what's going on so we can visualize it better. So, here we have an inclined plane. I'm actually going to draw it up here a little bit. Let's see. Okay, here's my inclined plane. And this angle alpha is, it says it's 43.1 degrees. And we have two blocks, M1, which is right here, M1, and M2, and they're connected by a rope passing over a pulley. So M1 is connected and M2 is connected. And that means that the acceleration of these two blocks will be the same. So M1 we're given is 22.0 kilograms. and we want the mass of M2. That's what we're trying to find. And so we can list our other givens here just as a way to be able to see them easily. Always list your givens, that is very important. So we have mu k, the coefficient of kinetic friction between M1 and the plane. Mu k is 0.30, and it's dimensionless because it's the coefficient of kinetic friction. And so the time here that we're given after it is released from rest, which by the way means the initial velocity is 0, the time is 2.75 seconds. And it descends 11 meters in the first 2.75 seconds. So I'm going to call that delta x, and that may seem a little confusing right now as to why I'm calling it delta x instead of delta y or something. But it's all going to make sense when we get further into the problem. I'm going to explain this, and it's going to make sense. Okay, so we have our picture. We've listed all our givens. We know exactly what we want. We want M2. So now, because it's a forces problem, we want to draw our free body diagrams. Yay! So, to draw a free body diagram, I'm going to divide my free body diagrams and clearly label them M1 and M2. So this free body diagram is going to be for M1. So we draw our point representing our box, right? And we want to identify all of the forces on it. And I always draw two free body diagrams, usually, when I have forces acting at angles, because I might want to redefine my x and y axes. If I don't want to redefine my x and y axes, if I'm fine with the coordinate system being relative to the page, then that will be clear and I won't draw two free body diagrams, I'll only draw one. But I think for this one we're going to want to redefine our coordinate axes. So for our first free body diagram relative to the page, for M1 we have the force of gravity, which I'm going to call Fg1, acting straight down from the box, right? Because it's pulling straight down on the box. And we have our normal force, right? Which is acting perpendicular to the plane of the ramp. And I'm going to call that N1. Because the normal force is always perpendicular, and in this case, the ramp is inclined. So therefore, this angle right here is alpha. Do you guys see that? Because it's inclined relative to the horizontal, and the angle relative to the horizontal is alpha. And so therefore the normal force, which is perpendicular to the plane, is at an angle alpha relative to the vertical direction relative to the page. So now that we have Fg1 and N1, let's identify the forces acting parallel to the plane. So we know that we have friction because the ramp is not frictionless. And we also know that that this system is moving like this, right? Because this block M2 descends after it's released from rest. So we know that M1 is moving this direction up the ramp. So therefore, the force of kinetic friction must be acting opposite that, and therefore it is acting down the ramp. So we have our force of kinetic friction like this, which I'm going to label Fk. And then because M1 is being pulled by M2, because they're connected by a rope, then we also have the force of tension this way, also parallel to the plane of the ramp, which I'm going to label T. Capital T for tension. So now that we have this free body diagram, which is essentially just this relative to the page, we're going to want to redefine our coordinate axes because that's going to make it a lot easier to solve this problem, right? And we also have our acceleration vector like this. So now what I'm going to do is I'm just going to rotate this free body diagram because I want I want all of these forces, these three forces, which are perpendicular, well, N is perpendicular to T and Fk, and Fk and T are parallel to each other, right? Acting in opposite directions. So it's going to be a lot easier if this Fg1, which right now is along the negative y direction in this free body diagram, it's going to be a lot easier if this force is the only one at an angle. So what I'm just going to do is I'm going to redefine my coordinate axes. You can define your coordinate axes any way you want. And you could leave it like this if you wanted. If you know how to work it out, you could leave it like this, as long as you're consistent. If you're consistent with your definition of your coordinate axes, and you can define your forces correctly, then it will still all work out. But it's going to be easier if we redefine our coordinate axes. So I'm going to draw my dot again for M1, and because we're rotating this by alpha degrees, then we know that the normal force, N1, is going to be pointing straight up. The force of tension, T, is going to be pointing to the right relative to the page like this, T. And the force of kinetic friction is going to be pointing to the left like this. So this is Fk. Now, what's Fg going to do? Well, because we're shifting this free body diagram by alpha degrees, this Fg also has to rotate by alpha degrees, clockwise. So we know that if this is the vertical, Fg1 is now going to be like this, and this right here is going to be alpha. So this is Fg1. And this is my positive x direction, this is my positive y direction. Okay, so now that we have this from making good progress, okay, so now that we have our free body diagram for M1, we can go ahead and draw our free body diagram for M2. And I forgot to mention this earlier, but G equals 9.8 meters per second squared, right? That's another one of our givens. It's implied even though it's not specifically given to us in the problem. Okay, so now that we have our free body diagram for M1, we can go ahead and draw our free body diagram for M2. And I forgot to mention this earlier, but G equals 9.8 meters per second squared, right? That's another one of our givens. It's implied even though it's not specifically given to us in the problem. And you might be saying to yourself, but Matthew, isn't G usually defined as negative since it's pointing in the negative y direction? And you would be absolutely correct! However, we account for this when we subtract our forces. We'll see later that Newton's second law tells us to add all our forces, but when we have G in the negative direction, the force of gravity in the negative direction, that's already accounted for when we subtract our forces. So when we define it, we want it to be positive 9.80 meters per second squared. Okay, so now we can go ahead and draw our free body diagram for M2. And so we have our dot, right? And we have the force of gravity acting on block 2, so I'm going to call that Fg2. And because it's connected by the rope, we have the force of tension upwards. Alright, now don't get confused here guys, because this confused me for a long time, for years, and I don't want you to get hung up on the same mistake. This is actually our x direction. We want to define this as our x direction. This is our negative x direction, because the acceleration is in the same direction as M1, right? They're accelerating together. So even though relative to the paper, the forces are acting in different directions, we can think of this rope right here we can think of that as the x-axis. So we can think about the x-axis starting from n1, going, passing around the pulley, and then that same x-axis now for m2 going in this direction. So this is actually our x and negative x directions respectively. And so that means that this has to be our y direction. Alright, so now that we've defined both our coordinate axes and our forces, we've identified our forces, now we can apply Newton's second law. And Newton's second law states that the sum of the forces acting on an object is equal to mass times acceleration, F equals ma. But that's only true for the x and the y direction separately, right? Because forces are vectors, and so we can only add them when they act along the same direction. So let's identify these forces here and put them in an equation. I'm going to start with the x direction. Actually, I'm going to start with the y direction. For the y direction, for both of these, we know that the acceleration is 0 for both of these, right? Because the acceleration only happens in the x direction. So the acceleration for y equals 0. And that's because for m1, we have n1, and then this angle right here, alpha, is going to influence this fg1, right? So fg1, so with a little bit of trigonometry, we can see that fg1y is negative mg cosine alpha, right? Because it's this component right here, and that's counteracting n1, but they're equal. So n1 minus fg1, sorry, that was a bad f. n1 minus fg1 cosine alpha equals 0. So we don't have to worry about the y direction for either of these, and there are no forces in the y direction for m2. So you don't have to worry about the y direction. However, for the x direction, let's identify the force for the x direction right here. So for this one, the force of tension T is acting in the positive x direction. So we have T, and by the way, after this I'm going to drop the arrow notation because I don't want to keep drawing arrows everywhere. T minus the force of kinetic friction Fk, and then minus, because the x component of Fg1 is acting in the negative x direction, right? So this is going to be minus Fg1 sine alpha. And we have sine because it's the opposite component of the force from alpha, right? Trigonometry tells us that this component right here is this force times sine of alpha. So we have minus Fg1 sine of alpha equals m1a, because this is m1. Alright, so that's great, right? Now for the x direction, for m2, I'm just going to label this right here, m1, m2, m2, sorry about that. Okay, m2, so we've defined our coordinate axes like this, right, with the x in the vertical direction relative to the paper. So we have fg2, which is positive, because according to our defined axes, it's in the positive x direction. So we have fg2 minus the force of tension T, which is acting in the negative x direction right here, equals m2a. So how do we solve for m2 from here? Well, we know that we can get a, so let's solve for that first. Using our kinematics equations, using our kinematics equations, we know that delta x, in our case, equals VIT plus 1/2 AT squared. And we know that VI is 0, right? Because that's given to us in the problem. It's released from rest. VI is 0. So really what we have is delta x equals, we have delta x equals 1/2 AT squared. And we know delta x, we know t, and 1/2 is just a constant. So we can solve for a. And I'm going to assume you guys are at least familiar with how to algebraically manipulate equations and solve for single variables. So this gives us 2 delta x over t squared equals a. Alright, now plugging in our numbers, we have 2 times 11.0 divided by 2.75 squared equals, let me just calculate this real quick. This is approximately equal to 2.909 meters per second squared, right? Because we're solving for acceleration. So this is 2.909 meters per second squared. That's the acceleration of this entire system right here, because both of these blocks are connected. So 2.909 meters per second squared. Okay, so going back to our forces formulas. So now we know A, and we're solving for M2. So really, we have our unknown in FG2, right? Because this is equal to M2G. So we have an unknown there, and we also have an unknown here in T. We don't know what the force of tension is. But that's okay, because we can find the force of tension. We can solve for it with the M1 equation, right? Because we know all of this stuff. We know M1, so we know FG1. We know the acceleration, we know alpha, and we can easily find the expression for the force of kinetic friction right here. And so we can solve for T. So bringing this down here, and solving for T, we have T equals M1A plus FK plus FG1, which I'm going to replace with M1G sine alpha. So this is our expression for the tension. And we can calculate this because we know that FK equals mu k, which is given to us, times the normal force M1. Now the normal force M1 equals, from up here, it equals FG1 cosine alpha. So plugging this into here, we have the force of tension equals M1A plus M1G cosine alpha plus M1G sine alpha. Alright, so now that we've derived our expression for the tension, it would be beneficial to perform something called dimensional analysis. If you don't know what dimensional analysis is, basically we look at the formula that we have, and we look at the units that it's going to give us, and we make sure that they're the same as what we want our answer. If it's not, then something's probably off. Either we have the wrong formula, or we've plugged in the units incorrectly. So what's this going to give us? Well, cosine alpha and sine alpha are dimensionless. They're not going to affect the units. A and G are both in meters per second squared, and M is all in kilograms. So that's good. That means that each of these are going to give us kilogram meters per second squared, which is in Newton, which is what we want because we're solving for a force. And that also means that we can add all these terms. So that's good. Alright, so let's plug in these numbers here. We know that M1 is 20 kilograms, so I'm just going to factor that out because it's a common factor in all of these terms. I'm going to factor that out, so 20.0. And by the way, I'm not going to be including units in my calculations. If you're new to physics, I recommend that you do, just so you can see it, but once you start solving complicated problems, then it's going to be a little bit cumbersome. So I'm not going to include any units in my calculations, but of course I'm always going to include units in my final answer. So 20 times, what do we have here? We have 2.909 plus 9.80 times cosine of alpha, which is 43.1 degrees, plus 9.80 times the sine of alpha, which is 43.1 degrees. Alright, and this should give us, hold on, let me calculate this real quick. So, my calculated answer here is 335.213 newtons. So that is the answer for the force of tension. And that's going to be true for both the tension acting on M1 and the tension acting on M2, because they're the same tension, or same force. So, bringing this one down here, we know that Fg2 minus T equals M2A. So that means that M2G minus T equals M2A. So this is good. That means we only have one unknown in this problem here. So I'm going to rearrange to solve for M2. So M2G minus M2A equals T. And factor out M2, we get M2G minus A equals T, divide by G minus A on both sides. So M2 equals T over G minus A. Alright, so let's perform dimensional analysis again. So T is in newtons, G minus A is in kilogram meters per second squared. So that means we have 1 newton, which is a kilogram meters per second squared, divided by meters per second squared, which is going to leave us with a value in kilograms. So that's good. That's exactly what we want because M2 needs to be in kilograms. So we probably have the right formula here. So let's plug in numbers here. So for our force of tension, what we got was 335.213 newtons divided by 9.80 minus 2.909. And this gives us a mass of, just a second, this gives us a mass of 48.605 kilograms, which in 3 significant figures is 48.6 kilograms. So this sounds about reasonable, right? Because our mass 1 was 22 kilograms, and so our mass 2 needs to be greater than our M1 because M2 is pulling down the entire system. So this sounds about right. 48.6 kilograms is our answer. And I realized that my calculations went off the screen, so here they are. So once we got our force of tension, we were able to calculate M2 because tension was our only, we calculated the force of tension at M2 was our only unknown in our force equations for M2. So I rearranged to solve for M2, and we got M2 equals T, the force of tension, minus G over A. And plugging in these numbers, we got the mass is equal to 48.605 kilograms, equals 48.6 kilograms. So that's our answer that we got. And it is reasonable, considering all our values here. Sorry about that. I will prevent that from happening in the future.